watching this presentation. So all good. Thank you. Okay, good. Right. So we can make a start. This is quite a chunky presentation. So like I say, try not to nod off, and hopefully we'll all learn something. If you've got a question, I should say as well, just drop it in the chat, and then what I'll do is at the end of the session, we'll circle back round and we'll pick up some of those questions if we've got time. I'm hoping not to keep you here for much longer than around 45 minutes. I think that's enough to be talking about flat roofing defects. Okay, so we're going to start now looking at the defects associated with specific waterproofing types. Obviously, the most common waterproofing types are felt, single ply, mastic asphalt, and liquids. So let's have a look at the defects associated with each one of those felts. So obviously we've got to identify felt, and normally these days it's mineral surface. It could be sanded, as is shown in the bottom right there, and also could be covered with chippings or aluminium paint, as you can see on the other two. But obviously the laps are there to give it away, to see what make sure that you can address it as felt. So the first and probably most common, I guess, and it's probably the thing that causes a lot of the other defects associated with felt, is mineral loss. So obviously the mineral is there to protect the bituminous substrate underneath, which isn't UV stable. So that's what the mineral or the chippings or the solar reflective paint are there for. And if any of that degrades and goes away over time, obviously these roofs are there to last a long time, and over time the mineral will degrade. It'll end up in the gutter, and then the UV will then start to attack the bitumen underneath, which causes cracking, as is seen in this one here. So cracks in felt, if they're small kind of cracks that you can see here, and this is due to age. Obviously this is probably an old Derbigum Alumask product here, which is designed to be left exposed, but over time it does degrade and start to crack, as will any felt that's exposed to UV. Just to look at the cracking in a bit more detail there. So on the left hand side of the screen, you can see the mineral has started to come away, and then the bitumen underneath has started to crack. You can also see a bit of delamination in that lap as well, which we'll come on to later. So that's cracking in the bitumen as well, that you can see that's oozed out, probably a torch-on system, or it could be a pour and roll system where the laps haven't been watered and the bitumen hasn't been taken away, but you can see the effect of UV on bitumen there. This one is obviously not down to mineral loss specifically, and this crack you can see kind of follows either the pattern of maybe the deck beneath that's moving, or the insulation beneath which is moving. So that what's happened here is over time the bitumen has become brittle. It started to move. Obviously this crack has developed now, and there's a nice weed or a tree growing out of the crack in this instance. So felt laps, obviously with your felt system, you've got laps there, and if they're not well bonded in the first place, they will delaminate. So delamination comes from two reasons. One is poor installation, and not sealing those laps well in the first place, and the second one is over time, like we saw, the bitumen can become brittle, that especially on old pour and roll systems. And over time, the laps can delaminate due to the movement of the building or the substrate beneath. Shaky video here, must have been cold on this site, but you can see that felt has started to delaminate. The lap has started to delaminate, and also as we pull on that, we can see that the felt isn't well stuck or adhered to the substrate beneath either. So that's obviously delamination of laps and obviously delamination of the felt as well, which is something that we need to be aware of. This is quite a common defect around outlets, especially where outlets have been attempted to be repaired, where there's no clamping ring in place, where there's no grate in place, so there's no way of securing that felt to the substrate. A good way, probably the safest way to detail or to refurbish felt around an outlet is to use what's called a refurbishment outlet, which has a spigot which sits into the existing throat of the outlet, and then has a felt flange around, which allows you to bond the waterproofing well. So this is quite a common defect, and obviously any water backing up from that outlet there, if the outlet becomes blocked, is going to get straight up and underneath the system, and then underneath the felt, and cause ingress into the building. Another example of delamination around an outlet. Here you can see this may have happened just over time, or it might have been there from the contractor not installing it correctly to these cast iron downpipes. And this is what we saw, obviously, inside the building. So we can see that this is the outlet, or this is the downpipe coming through there, and you can see the ingress around all of those outlets. So it's another thing to say: have a look inside first when you're surveying these. Have a look at the downpipes, especially if it's an internal drainage, and then obviously you can reflect that when you survey the roof. So when I spoke earlier about clamping rings and things like that, this is what kind of good practice looks like in felt. Obviously, you would star cut the felt there, adhere it to the bowl of the outlet there going down, and then we'd have what's called a clamping ring. So you've got that bar over the top there. You put the clamping ring in place, which you can see in the top left picture, and then you tighten that nut on the top of the outlet grate, and that creates a watertight seal then at that outlet. We spoke earlier about refurbishment outlets. That's just a diagram there. You can see the spigot that would fit inside the existing downpipe. It's got a rubber O-ring or some other sealing device, fins or something like that, that stops water backing up and going over the top, and then that felt flange there is adhered to the existing waterproofing or the new underlay, and that forms a watertight seal. So that's a good way of refurbishing internal outlets on felt. Okay, on to the next defect. We're looking at blistering here. Blistering is notoriously difficult to get a good picture of, so I try to use some kind of ruler or something like that to show that the blister is in place. You can see it's just another kind of image of it there. And if we cut open that blister, so there's a couple of different types of blisters that we see in felt: an air blister and a water blister. Fairly self-explanatory. One's caused by air expansion within the build-up, and that might be there from day one. It might come from any kind of insulation, and it also comes from let's say outgassing of insulation. If there's any kind of moisture within the build-up when the system is installed, then through solar gain and everything, these blisters can appear, and then they can disappear when it becomes dry, when it becomes cold as well, I should say. So heat, expansion and contraction will cause these blisters to rise and fall. Air blisters, let's say, they can be there from outgassing from insulation, and if the contractor hasn't used some kind of vapor dispersion layer or a 3G in the old days to allow vapor to disperse around the system. So what we would do on a survey in this situation is, if if we're fairly certain that this is an air blister, in this instance, we've cut it open. We'd take a moisture reading in this place, and obviously, as you can see in this instance, this is dry. Sometimes they're nothing to worry about. They're always something to keep your eye on as part of the annual inspections and things like that, how bad the blistering gets and everything like that. But over time, expansion and contraction, like I say, the rising and fall of the blistering can cause the felt to crack, but it's something that you just need to keep your eye on, not necessarily going to cause water ingress. This, on the other hand, is a water blister. There's a small blister there. You can see the felt kind of moves around like a waterbed. This is a better kind of illustration of that. You see, this is a large blister, and this is where water has got into the system and is sitting, in this instance, between the cap sheet and the underlay. So there's chances are that there's a delaminated lap or some kind of detailing issue where water has got into the system. We can usually trace that back by walking on the blister, and the water will usually squirt out in some instances. I wouldn't always recommend taking a core sample in these areas, but if you happen to, obviously you've got to make sure that we seal that up and everything like that. But that's kind of what happens in some instances when we do take core samples, and there's water present within the system. Okay, so moving on to single ply. I'd say identifying single ply is fairly easy. It's smooth. You can see the laps on the system there. You can usually see some kind of mechanical fixings, or the kind of impression of the mechanical fixings, and that's all completely normal when it comes to single ply. As we said in the last presentation, there's a couple of different types, plastics and rubbers, all different kinds of plastics. They're just three of the most common. An EPDM is usually black in colour, which is a rubber membrane that's used as well. Single ply membranes, obviously mechanically fixed, fully adhered or ballasted. So when we're looking at defects, we need to try and identify kind of fastener types and everything like that. So there's three kind of different fastener types. One is the one in the top left there, which is used to mechanically fix the insulation. Sometimes that's a washer where solvent is used on the top of the washer there to bond the insulation to it. So that's when you see the impression of those. So either solvent welding or solvent bonding or kind of infusion welding as well. The top right there is a bar system, which is used in roofs with high wind uplift risk. So they'll mechanically fix those bars across the system to better hold the single ply down. And the bottom one there is a lap, mechanically fixing the laps. So they'll put a fixing every however many millimeters defined by the manufacturer, and then they'll weld the system over the top, as we saw in kind of in session one. Just an example of a roofing system with a bar layout. So like say in areas of high wind load around the perimeter zone, you'll see more bars, you see more fixings, like we said in the last. So a common defect, obviously, with the system being mechanically fixed, if it's poorly fixed, then that's a fairly common defect in single ply systems. So make sure that the fixings incorrectly. Obviously, this one is a poorly fixed insulation washer, in insulation fixing. Shall we say? You see the washer there on the top. And obviously, when we've walked on this single ply system, you can feel that movement underfoot. So that's why we've done a bit of a core sample investigation here to see what we've got. As a consequence of that not being mechanically fixed properly, you can see that there's a void there between the metal deck and the insulation. And when we press down on that, the insulation is bowing in those areas due to it not being mechanically fixed correctly. So a bit of a video here to show what happens in the event that the single ply isn't mechanically fixed and it isn't fixed correctly, you can see the kind of effects of wind on the roof there. So these are some pictures of that particular site. So you can see the fixings are starting to protrude through the membrane there, and they have pierced the membrane in several areas, which obviously is resulting in this roof being leaky. It's not just the field area that we need to consider with single plies. Because it's a mechanically fixed system, it's also mechanically fixed or restrained at the upstands and any kind of interfaces and everything like that. So we need to also check those, make sure that it's fixed correctly in those instances. So obviously an example of where it's not. Say another example there of where it's not been correctly fixed at an upstand detail underneath a sill. More areas where it's not been fixed correctly or not been adhered correctly, just not been installed in a good manner in those in that image, really. Like I say, kind of the consequence of not mechanically fixing, not doing wind uplift calculations correctly and everything like that. This roof is obviously blown off, and that's what can happen with these kinds of systems. Just another kind of example here. This isn't me on this roof, by the way. I think I would be I was sent this video. So yeah, that kind of gives you the idea. You can see the laps of the single ply starting to open up there, and obviously eventually the wind's going to get underneath there, and this roof will end up probably in the car park. So with single ply, lap delamination is almost always down to installation error. So if we don't make sure that we've welded those laps correctly, then they can delaminate over time, or they just weren't laminated correctly or welded correctly in the first place. So this is something that we obviously look for in our surveys. Single ply, obviously, with it being a welded system with lots of seams around details, detailing penetrations, pipes, all that kind of thing, is something that we need to carefully look for and make sure that it's welded correctly in those instances with the hand welder and everything like that. So make sure that around upstands and details and everything like that, that it's well bonded. It's very rare to see air blisters in a single ply system, although you can do with systems that are fully bonded, but more often than not, single ply systems are not fully bonded, not fully adhered, because they're mechanically fixed. That's the beauty of it, making it a fast, clean installation. So if we come across blisters on a single ply roof, it's usually a water blister, like we see on there. This is quite a rare defect, so I say it's not really a common defect, but this is kind of loss of plasticizer, and this can be down to unknown reasons, as well as kind of plasticizer migration. If we don't use a separation layer between a single ply and something that's going to take those plasticizers away, then this can happen. It can also happen as well when we overlay a single ply with certain liquids that haven't had compatibility testing, or a barrier primer isn't put in place. That can cause what's called plasticizer migration, and that can cause the liquid over the top of it to soften, or the single ply beneath it to crack, which is what we see kind of in this instance. Like I say, this isn't a common defect, but I thought I'd just put this one in for dramatic effect. Mechanical damage, obviously single ply is one layer, as the name kind of gives it away. It's a single layer. It's usually between 1.5 and 2 millimeters thick. So where you've got a lot of plant on a roof where it needs maintenance and things like that, these people who maintain it can leave screws and things on the roof. If they get stood on, then mechanical damage can occur easily on single ply. Like I said, it is one of those things that we need to be aware of with a single ply system. So you can see all of the patches, particularly on this roof area. Okay, so moving on to that's kind of the common defects of single ply. Just moving on to mastic asphalt now. Mastic asphalt is fairly easily identified. It's solid when we stand on the roof. It's usually covered by chippings or solar reflective paint because it is exposed to the to UV. Obviously, it's a bituminous product which is susceptible to UV. So on with asphalt, there's a couple of things when it comes to blistering, or bumps, as they're sometimes known as with asphalt. So bumps are just as it's kind of as the title kind of gives away. It's a bump in the asphalt, and it might be small. And a bump in the asphalt can be caused by installation stage. So maybe the first layer wasn't dry. Or maybe when they install mastic asphalt, they put cement dust into the metal buckets to stop the mastic asphalt from sticking to the buckets. So when they pour that out, sometimes you can get little pieces of the cement dust, which can then expand underneath the asphalt and cause what's called a bump. Now with mastic asphalt, one of the beauties of it is it's very easily repaired. So if you do see those bumps in your kind of annual inspections, those bumps can be warmed and smoothed, and they'll usually go away. When it becomes an issue, I guess, with mastic asphalt is when it becomes a blister. And what you can see there is the cracking within the blister. So again, that might be caused by lack of screed vents, moisture within the system, the substrate not being completely dry, all these kinds of things that would cause moisture underneath the system. So another kind of extreme example of a lot of blistering in mastic asphalt, like I said, this can be caused by the first layer not being dry, or kind of lack of screed vents. Cracking is something that we see in asphalt. This kind of happens over time, or certainly in older kind of oxidized asphalt systems before kind of SBS and other kind of modifications were introduced to make it more elastomeric and more stretchy. But over time, obviously, asphalt can lose these properties, and over kind of movement joints and things like that with expansion and contraction, it can start to crack due to age. This is quite a common one where you've got at the edge, you can't actually see what you've got there, but you've got an aluminium trim. Obviously, the aluminium is metal, so it will expand and contract at a greater rate than the asphalt. So you kind of see a crack every kind of 3 meters, which is the kind of general length of the aluminium drip trim in this instance. So that's just something to have a look out for. Again, cracking along movement joints and things like that. Cracking in corners, cracking at upstands, all of these kinds of things. The detail, like I always say, the devil is in the detail when it comes to any kind of survey. So make sure that we're having a look at all the details and everything. Make sure that we're looking for all those cracks. Slumping details, again, if it's the heat from the sun obviously causes this. This is more common in south-facing kind of upstands. In this kind of upstand, you can, or you should really use a metal lathe before to install the asphalt onto, which would prevent or certainly slow down this slumping, and would give the asphalt more of a key to adhere to. Also, the asphalt should be installed in 2 coats, which again might have prevented this issue. But you can see in this instance, the asphalt has slumped at the upstand, and also at the drip detail as well. So this is just a case of aging with asphalt. Softening of the asphalt as well is something that we do see. So obviously on this roof, there's been some kind of air conditioning units or something installed which have been decommissioned and removed. You see kind of the rippling as well, kind of to the bottom left of that paving slab there where the air conditioning units have been on. So that's caused by the asphalt starting to soften, and then the vibration from the plant or from the air conditioning units has caused that rippling in the asphalt as well. And again, softening. So this is obviously an age-related issue where a plastic downpipe, even like the little weight of a plastic downpipe over time has caused that to soften and to dig into that. This is called thermal shock. Again, it's one that we don't see too often, but it's one that we need to be aware of so that we can diagnose it when we come to do our surveys. So what is it? Well, according to Wikipedia, I'm going to read this. Thermal shock is a type of rapidly transient mechanical load by definition. It's a mechanical load caused by a rapid change of temperature of a certain point. It can be also extended to the case of a thermal gradient, which makes different parts of an object expand by different amounts. The differential expansion can be more directly understood in terms of strain, in terms of stress, and it shows. Okay, so what does that mean when it comes to roofing? So thermal shock in roofing was first seen when the warm roof was introduced. So what that actually means is, we've got the structural deck, as we said in the last presentation. We've got the structural deck, we've got a vapor barrier, we've got insulation, and then in this case we've got the waterproofing is asphalt on the top. So in the olden days, before modified asphalts and things like that were out, what would happen is the heat of the warmth of the heat from the sun would be absorbed into the asphalt and into the insulation. At night, then obviously the sun goes down, the temperature changes, it becomes cold, but the insulation is still restoring that heat, acting as a heat sink. So the temperature on the outside is lower than the temperature on the inside, and that's what causes the thermal shock. Hope that makes sense. Okay, so liquid, different. Like I say, there's lots and lots of different chemistry types with liquid. So it's difficult to kind of say what common defects are, because firstly you need to know what kind of liquid has been used, and to identify that it can be difficult to the untrained eye, but we can kind of tell sometimes what kind of liquid and what chemistry has been used in order to identify these. So again, there's 2 different types of reinforcement when it comes to liquid. One is your glass fiber reinforcement, and one is a polyester fleece. In this instance, we can see it's a glass fiber reinforcement. So one of the common defects of glass fiber reinforced is the film thickness of the top coat. So you can see here, probably the base coat as well here. This is just this is a shambles. This one is, because you can just see the glass fiber reinforcement. You shouldn't be able to see this when you come to inspect a liquid system. You should hardly be able to see the glass fiber reinforcement, because it should be well embedded in the base coat, and then a top coat goes over the top. So really, if you can see any kind of glass fiber reinforcement to this kind of extent, then obviously that's an issue. Pinholes, this again something that we need to look out for. It's quite common in most types of liquids, and this is caused by the base coat being installed, and maybe moisture pockets within the base coat. moisture pockets within the glass fibre reinforcement, and then the top coat being installed over the top can be caused by overactive use of the roller. There's all different causes of pinholes, but you can see the kind of the effect of a pinhole there. What will happen is pinholes will suck water into them, and then over time through freeze and thaw cycle, it'll expand and contract, and eventually it will cause delamination. So pinholes are something that we should really look out for right at installation stage. They can be easily rectified at installation stage by using more material, by using some kind of filler to put into the pinhole or whatever. And that's obviously down to the manufacturer to tell you how to remedy those pinholes when you're inspecting and snagging the work. Again, that's just another example of pinholes. This example here, you can see the liquid has been installed. Probably it hasn't been evenly rolled out, so you can see what's called a bow wave here. And within that bow wave, you can see pinholes there have been caused by the liquid being too thick at the end, so it's not been evenly leveled off with the roller. Cracking usually takes place within a rigid GRP system. So let's say you've got all your different chemistries. So you've got your rigid kind of GRPs, you've got your flexible GRPs as well. But like I say, cracking is usually associated with rigid GRPs, and under film thickness and over film thickness is usually the cause of the cracking with here. Like I say, it's a rigid material, and if it's installed over a system that over a substrate that moves a lot, then cracking can take place. And it can also be down to lack of reinforcement, not enough reinforcement in this instance. So you can see here what's happened. This is a gap in a trim, or a joint in a trim. You can see there has been reinforcement used, but in this case, the manufacturer calls for double reinforcement at any kind of joints in trims and things like that. So that obviously hasn't been adhered to here. Some others will put like a polyester bandage in, or a flexible bandage, to make sure that the cracks or the trim expansion and everything is taken care of. Wicking, again, is another kind of common defect, only with glass fibre reinforced systems. So what this is when the base coat is installed and the glass fibre is embedded into the base coat, especially around details, the installing contractor should make sure that there's all of the glass fibre reinforcement fibres are well embedded and not sticking out in this instance. Once the base coat has cured, again, it should be checked and snagged, and these wicks should be sanded off and got rid of. In this instance, they haven't been, and the top coat has been installed over the top. What that will cause, and why it's called a wick, obviously, is moisture will then travel into the system, because the glass fibre reinforcement is really, it's a very, very, very small straw, or a tube, if you like. Them glass fibre, the fibres are actually hollow, so what that can do then is wick moisture into the system, and again freeze and thaw over time, and eventually that can cause the liquid to delaminate. So wicks is something that we need to obviously make sure we're having a look at. Whether you can call this wicking or just shocking is probably a better word for it. This is just obviously poor workmanship, where the glass fibre reinforcement has not been done properly. I say delamination. In this instance, probably down to poor preparation. So one of the most important things when it comes to a liquid membrane is correct substrate preparation, making sure that substrate is clean before we install anything onto it. And that goes for the substrate itself, to make sure that it's clean and primed so the base coat sticks to it. And also intercoat contamination can happen as well, which is probably what's caused this. So when the base coat is installed, the manufacturer will prescribe a certain window as to how quickly you've got to get your top coat on the top of that. Or it will need to be cleaned again. Sometimes it will need a reactivation primer or something like that. Sometimes it will need an acetone wipe to make sure that top coat sticks to the base coat. And if there is any kind of intercoat contamination, then this is an extreme example of what can happen. But you saw the kind of delamination that we can see. This kind of thing is kind of exclusive to any kind of system that needs kind of a catalyst, multiple parts. And this what causes this is incorrect catalyst levels, and then the membrane will never actually cure, and it will stay soft for its life. So that's one that we need to look out for as well if we see any kind of soft liquid membranes. Okay, so all of those defects that we've just had a look at are kind of exclusive to those materials. These are more like construction defects or other kind of defects as well that we see, which can be associated with any waterproofing material. So they're not exclusive. So poor detailing and retrofitted items, I'm going to say here. So workmanship, obviously poor detailing is probably the biggest cause of defects in flat roofs. Materials aren't manufactured to leak, and it's only when they're installed. So it's important to use a qualified contractor, reputable contractor who's trained in the system that's being specified. Again, retrofitted items are something that we need to make sure that we're looking at. So in this instance, the cladding has been installed. They've cut away the waterproofing and mechanically fixed the cladding into that probably through the waterproofing system. So just when you're getting any kind of retrofitted work done, any kind of refurbishment done to any area, it's important not only to consider what you're having done, but also consider the effect that may have on the existing roof system that you've got in place. We looked at this before. This is a really common thing that happens is obviously you have air conditioning units installed on the roof or plant, any kind of M&E equipment that's installed and retrofitted. You get your electricians or whoever comes along and they just drill a hole through the waterproofing. They'll squirt some expanding foam in there or put some kind of temporary bandage, some kind of flash band over the top, and then obviously over time that's going to leak. So make sure that again, when we're having our M&E equipment installed, it's done in the correct manner. Involve the original manufacturer if there's still a guarantee in place, and make sure that it's done to a good standard and inspected by either the manufacturer or somebody independent. Flash band, again, it's Bodget and Scarpa's favourite material, isn't it? But it's my least favourite material for waterproofing or for temporarily waterproofing these kinds of things. I say in this instance, the waterproofing should have been taken onto that metal flange and up underneath that upstand and protected underneath the witch's hat kind of detail there, and it hasn't happened. So this roof is leaking. Again, air conditioning systems, a favourite is to just drill through the roof like curb. Bodge it again with some liquid, and it's going to stay watertight for a while, but obviously it's not a watertight solution for the end. So what I'm going to say is 9 out of 10 times a flat roof will fail at the details. It's usually down to workmanship. There are a few general guidelines good to keep in mind. So upstand height should be a minimum of 150 millimetres above the finished level of waterproofing. That's obviously according to British standards. There are times when we can accept less upstand heights. But again, that needs to be qualified by the manufacturer. The material should be chased into a suitable upstand. So where it comes to an upstand, there should be a chase cut and the waterproofing material taken into that chase and then sealed and protected. If that can't be the case, then exposed edges should be protected at upstands that can't be chased, or a termination bar or something like that, to make sure that the waterproofing isn't going to come away from that upstand. And obviously material should be suitably terminated at perimeters. This is an aged asphalt roof here, and you can see there's no edge trim or anything that's been installed in this instance. It may have been in the first place. I'm just obviously using this as an example to say a perimeter detail, we should either have a welted drip detail or some kind of trim detail, and in this instance it's not the case. Again, here's an example of where a felt system has been installed, but it's not been correctly chased and wedged into the brickwork mortar joint there. So what should have happened, as we said, is that mortar should have been chased out. The felt should have been taken inside, wedged and kept in place, and then some kind of flashing detail also inserted into that chase and wedged and sealed correctly to make sure that it's a good detail. Again, just an example here that where it's a kind of a retrofitted thing that's happened. So on the face of it, looks okay. The parapet, the coping stones have been installed on the top. The mortar has been renewed because the client had water ingress down the sides and above at the window heads and everything that are below this detail. So somebody's come along and they've repointed the joints, but then obviously when we've looked a little bit further, this is the bottom of that coping stone. There was a felt system. They've had a liquid system installed, again a rigid GRP system in this instance, and what the contractor has done is just shoved these flashing details into where he's cut the felt away, not any chase or anything, and then just kind of bonded and sealed it and everything, and put some kind of mastic detail on here. So water is actually flowing off the top of those coping stones, as you can see there, underneath and then down the system. So that's another one. Again, you can see there that flashing detail hasn't been correctly installed. So there you go. Again, same project, but a brickwork detail. This is just pay attention to the details, because on the face of it, this may look okay. So the flashing has been chased into the brickwork there. You see it's nicely sealed, but what they've not done is flush pointed the brickwork prior to installing this, so water can actually get down the back of that brickwork there at the perp ends. And like I said, they should have really flush pointed that brickwork first or after. Okay, existing drainage and roof falls, something else that we need to consider as a common defect. So in refurbishment, like I said, these refurbishment outlets are good when they're used correctly. However, in this instance, they hadn't. So what had happened here is they've installed an EPDM roof. They have installed the refurbishment outlets, but the original outlets were around 150 millimeters in diameter, and they've installed 60 millimeter diameter outlets, and obviously that's caused a problem with the drainage in this roof, because they've severely kind of reduced the capacity. Again, what we're saying on a flat roof, existing falls need to be determined when we're surveying a roof. If there's excessive standing water or evidence of it, this can have a detrimental effect on the structural loading. And just as a rule of thumb, a millimetre of ponding water weighs about 1 kilogram per square metre. So it's a hefty weight, and obviously as decks can deflect, then that can become more. So on this one, you see the ponding water there is about 20 millimeters in the middle of the roof. So we've got about 20 kilograms per square meter of additional load on this roof. You can see the outlets on this one are down the perimeter of the roof there. You can just see one about 3/4 of the way up the picture. But the falls are actually now going away from those outlets. And when we look on the inside of the building, you can see the effect that it's having. This is a block and beam concrete deck, and you can see those structural beams there starting to bow. So it's quite important. It's actually more than that. It's 70 millimeters of ponding water, excuse me. But so again, you can see it's 70 kilograms of water per square meter, which you can see kind of stands to reason. So it's important that we get that water off that roof, and that we redesign something, a tapered insulation scheme or something like that, to make sure that we get that water off that roof. That's what good falls looks like. So you can see on this roof here, you've got the gutter, which is on the left-hand side of the picture, and you can see the upstand height there increasing as we get to the gutter, which shows that there is a good fall on this roof. And the opposite of that, you can see there isn't a good fall on this roof with the spirit level there, which is what's causing the ponding water to sit at that drip edge detail. Condensation risk, something that we just need to consider as well as part of our survey. It's not always a leaking roof, so interstitial condensation, that's something that can happen. Obviously, it happens when warm air from the outside meets the cold air from the outside meets the warm air from the inside, and within any kind of roof system build-up, you have what's called the dew point, which is where those two internal and external temperatures meet. And that's the point of dew, which is the point where condensation occurs. So through condensation risk analysis calculations, we can determine whether there's a condensation risk in this building. You can see there that they've installed an OSB deck over an existing built-up felt, and then put a GRP system over the top. This is a cold roof construction, which isn't recommended now, like we said, by BS 6229. So you can see that ventilation isn't in place, and there is a condensation risk in this. Ways to avoid condensation, especially in a warm roof, is to install enough insulation for a start. So anything kind of over 60 millimeters of insulation will kind of negate a condensation risk. Obviously, we should be installing insulation greater thicknesses than that to achieve current U values in accordance with Part L of the building regulations. However, on existing buildings, you should be looking for something around 50/60 millimeters, and the addition of an air and vapor control layer. And in this instance, you can see there is no vapor control layer in place when we've done a core sample. So this leaky roof that the client saw in this instance wasn't actually a leaky roof. He had a condensation issue. So you can see the condensation risk in the analysis in this instance. So you can see that's quite a peak build-up, and obviously worst case scenario. So in this instance, the condensation never has a chance to dry out, which is why the water or the condensation is starting to drip down the inside of the building in this instance. So what's the cause of these common defects that we see? So poor design, so wind loading, condensation risks, U value calculations. Make sure that we've got the design right. Like I say, these for me are the 4 pillars of a good roof. I've actually wrote articles on the 4 pillars of of a good roof or a watertight roof. So have a look on my LinkedIn profile if you want to read those articles. So yes, so poor design, poor material selection. So let's say, have we selected felt, for an example, on a highly detailed roof where a liquid might be better? Have we selected single ply on a ballasted roof where a fully bonded system might be better? Only my opinions, by the way. Don't hang me for it. Again, poor installation is something that we've certainly looked at during this, and lack of inspection / maintenance is something that I just want to come on to. So obviously this is a lack of inspection, lack of maintenance. The outlet has become blocked. As a consequence, possibly, of the outlet being blocked, the laps have started to come apart through freeze thaw, and again the water, or the felt, I should say, started to delaminate at the outlet, and water could get back up underneath here. Again, inspection, maintenance, weeds, all kinds of vegetation can start to grow. This should be removed on an annual basis to make sure that you're getting the most out of your roof, and obviously clearing gutters and everything like that. That should be just part of your annual maintenance. Why are these inspections important? Well, most manufacturers will have a clause within their guarantee, which you can see there, that says according obviously to British standards. So the manufacturers are doing nothing wrong here in putting this there in their guarantees, but it says it needs to be maintained and it needs to be inspected on at least an annual basis. Some say twice annually. So make sure that a competent person is carrying out these warranty inspections. They are invaluable. Okay, so any kind of relevant documentation that we've referred to here, BS 6229 is kind of the Bible, if you like, for the flat roofing installation. BS 5250 will deal with your management of condensation, air and vapor control layers, things like that. We have referred to Part L of the building regulations in this instance, which is the thermal calculations. There are obviously other parts of building regulations that apply to flat roofing, but we haven't referenced them in this presentation. If you've enjoyed this, or if you are enjoying this, then I can come into your practice or whatever and deliver a CPD to your colleagues, or either in person or over Zoom or over Teams, which we can do. Let's say we can put a course together for your choice. Services available from me, full condition surveys, detailed condition reports, anything that you need when it comes to flat roofing, metal roofing, any kind of roofing. We can come and have a look at that and give you a professional opinion, put reports together and everything like that. I'm just going to leave my contact details on the screen there for you to scribble down, and I'll have a look. No questions have come in on the chat. So if you've got any questions, if you want to unmute your microphone and ask away, or if you want to just type it in the chat now, then we can have a bit of a Q&A session. We've just got 5 minutes, so thank you, Luke. Is there any way to prevent cracking to the asphalt at the edges of balconies with lead/aluminium drips trims? Well, the thing is that aluminium trims, obviously lead trims aren't really a thing, but aluminium trims are becoming less and less kind of common these days. You see more GRP trims, but like with a drip detail with asphalt, normally there wouldn't really be a trim in place. It'd be more your water check details. So your water check details, again, you probably use a GRP trim these days. But like I said, those kind of cracks that we do see are kind of aged So it's like aged asphalt. Before it was polymer modified. More modern asphalt doesn't crack as much when it comes to metal flashings and things like that. So that's improvement in the product has probably negated that. That's probably a legacy kind of common defect that we see with aged asphalt roofs. And it's not just asphalt, it's kind of any kind of bituminized system as well. You'll see that with felt as well, where the UV will get to the felt. It will degrade over time. It's just a thing that happens, and it can happen over 15, 20, 25, 30 years. And that's just a common defect because of age, really. Nothing wrong with the product. I'm waffling now. Any more questions, guys? I'll just stick around for 1 more minute just to give you a chance. Hopefully, like I said, you've enjoyed it. This will be uploaded to our YouTube channel. So like and subscribe, as they say. Okay, I don't think there's any more questions. Thank you, guys. I hope you've enjoyed that. Session 3 is in a few months' time. If you want to jump on that one as well, the registration is open. I think by registering for this, I think you've automatically registered for that as well. So hopefully you have enjoyed this. Have a good day, and I will see you on the next one.